Duncan and Toor in 1962 published a set of diffusion experiments conducted in a two-bulb diffusion apparatus connected by a 2 mm capillary tube. The initial compositions in bulb A and bulb B are indicated here. Interesting to note is that the nitrogen mole fraction initially is 0.5 in both bulbs, and therefore there is no driving force in terms of mole fractions for nitrogen. At time t is 0, the stopcock connecting the two bulbs is opened and interdiffusion is allowed to take place. The equilibration trajectories for hydrogen and carbon dioxide in bulbs A and bulb B follow the classical exponential increase and decrease that is to be expected as the bulb compositions approach equilibrium. The continuous lines shown here and the dashed lines shown here are the solutions to the Maxwell-Stefan equations using the data on the Maxwell-Stefan diffusivities determined from the kinetic gas theory. The equilibration trajectories for nitrogen in bulb A are indicated by the red circles, and in experimental data for equilibration in bulb B are indicated by the open circles. It is interesting to note that despite the fact that the initial compositions of nitrogen in the two bulbs A and B are the same initially, the fluxes of nitrogen in bulb A and bulb B are non-zero, and this causes the approach to equilibrium in bulb A to exhibit a minimum and in bulb B to exhibit a maximum before eventually they equilibrate to the same compositions in the time interval between 0 and 6 hours. We experience the phenomena of uphill diffusion for nitrogen. And what is notable is that the bulb B has a higher mole fraction of nitrogen, but this continues to increase at the expense of composition of nitrogen in bulb A. In other words, nitrogen is being pumped from bulb A to bulb B, and the reason for this in physical terms can be appreciated if we note that carbon dioxide in bulb A is initially 0.5 and in bulb B it is initially 0. The drag between nitrogen and carbon dioxide, which is 1 divided by the Maxwell-Stefan diffusivity D23, is large, and therefore the friction between nitrogen and carbon dioxide has the effect of dragging nitrogen from bulb A to bulb B. At this time, we note a plateau in the compositions. So even though there is a large difference in the mole fractions in the two bulbs, the the flux of nitrogen at this point is 0 because the concentration profiles show a maximum here. And beyond that point, normal behavior manifests, and the two compositions in bulb A and bulb B approach one another to finally reach equilibrium at very long times. The continuous red lines and the dashed red lines represent the solutions to the Maxwell-Stefan equation using the data on the Maxwell-Stefan diffusivities determined from the kinetic gas theory. Indeed, in this paper cited here, Joseph Stefan anticipated the occurrence of uphill diffusion in ternary gas mixtures using a formulation that is almost identical to the ones we use to solve and obtain these calculated profiles. The experimental data of Duncan and Toor measured in the two-bulb diffusion apparatus is plotted in ternary composition space in the red circles denote the equilibration from the initial compositions to the final equilibrated composition. The green squares show the plots of the experimental data in bulb B as it progresses from the initial state to the final equilibration state. The continuous green and red lines represent the solutions to the Maxwell-Stefan equations. If the diffusion process is assumed to be uncoupled, in other words, the flux of each component is taken to be proportional to the mole fraction gradient of that component with a proportionality constant di that is independent of composition, then the equilibration trajectory would follow a straight line drawn by the dashed black lines. The serpentine equilibration trajectory is a signature for uphill diffusion and will be observed in several examples that will follow the slide. We ask ourselves the question whether the interdiffusion of the ternary gas mixture in the two-bulb diffusion experiments of Duncan and Toor violates the second law of thermodynamics because of the uphill transport of nitrogen. The second law of thermodynamics mandates that the rate of entropy production be positive definite. The entropy production for the ternary mixture is given by this expression where J1, J2, and J3 are the diffusion fluxes of hydrogen, nitrogen, and carbon dioxide. And these represent the gradients of ln x1, ln x2, and ln x3, where x1, x2, and x3 are the mole fractions. For uphill diffusion of nitrogen, this term this contribution of this term is negative. In other words, nitrogen consumes entropy. This is not disallowed because hydrogen and CO2 produce entropy at such a rate that the overall rate of entropy production is positive definite.